A mysterious, bright flash recently observed by the Zwicky Transient Facility appears to be a black hole jet pointing straight toward Earth. Earlier this year, it detected a unique flash in a region of space where no such light had been previously observed. Rough calculations show the flash gave off more light than 1,000 trillion suns. The flash appears to come from a region where a black hole ripped apart a star, consuming it and shooting a jet of stellar leftovers at near light speed directly toward us. The destruction of a star by a black hole creates something astronomers call a tidal disruption event, or TDE. This TDE is dubbed AT2022 CMC, and is the most distant observation of a black hole tearing a star apart. The event occurred about 8.5 billion light-years away. That's practically halfway across the universe. The destruction of a star by a black hole creates something astronomers call a tidal disruption event, or TDE. Such TDEs happen when stars get too close to black holes, and the black hole's tidal forces tear the unlucky star apart. In about 1% of TDEs, black holes shoot jets of plasma and radiation from their poles. Such events are very poorly understood because we found only a handful of them. So finding them is very important for us to understand how the jets form and why they occur in such a small fraction of TDEs. Such bright flashes are also very useful ways of detecting supermassive black holes, which are thought to exist at the center of most major galaxies, if not all of them. The biggest black hole ever found lies at the center of the Phoenix Cluster, a group of about 1,000 galaxies located in the southern constellation of Phoenix, about 5.8 billion light-years from Earth. The South Pole Telescope collaboration found this cluster in 2010, and it's one of the most intensely studied galaxy clusters in our universe. At the heart of it is what scientists believe to be the biggest black hole known to humanity. Known as Phoenix A, the supermassive black hole is about 100 billion times more massive than the Sun. That's a number that our brain simply can't understand. This black hole is actually more massive than some galaxies, and about 10% the mass of the entire Milky Way. Calculations show the diameter of the black hole is about 590 billion kilometers, or about 100 times the distance between the Sun and Pluto. Black holes don't just eat stars, they also boost star formation, and galaxies in Phoenix A cluster have an abnormally high rate of star formation, over 700 times higher than the Milky Way. While the Milky Way gives birth to about 1 star per year, Phoenix A births 740 stars every year. But the most active galaxy is a massive galaxy right at the center of the Phoenix Cluster, which is surrounded by hot gas millions of degrees in temperature. Scientists calculated that this gas has a mass about trillions of times that of the Sun, or several times greater than the combined mass of all the galaxies in the cluster. This hot gas loses energy as it glows in X-rays, causing it to cool and form stars. But usually it's the other way around, because in most galaxy clusters we have observed, bursts of energy driven by such a black hole keep most of the hot gas from cooling, slowing down star birth. The first clear evidence of rapid star formation in the Phoenix Cluster was reported in 2012. Then, NASA's Chandra X-ray Observatory found the hot gas is cooling nearly at the rate expected in the absence of energy produced by a black hole. However, later on, Hubble data show that about 10 billion solar masses of cool gas are located along filaments leading toward the black hole. Additional radio data come from the Very Large Array that reveals jets blasting out near the central black hole. Scientists believe these jets likely inflated cavities or bubbles in the hot gas seen in the Chandra data. Both the jets and bubbles are evidence of the rapid growth of the black hole in the past. Scientists expect that early in this growth, the black hole may have been undersized compared to the mass of its host galaxy, and too weak to heat the surrounding gas, which eventually got cooler. The farther away from the black hole, the faster the gas can cool to form stars. Eventually, the black hole jets will generate turbulence, sound waves, and shock waves that will heat up the gas until the outburst ceases and the gas starts to cool again. Phoenix A star's supermassive black hole is so massive that it would have been impossible for it to form from a star. The most likely scenario is that it formed from the collision of multiple supermassive black holes that formed shortly after the Big Bang, meaning it is one of the oldest black holes in the universe. Webb truly is a cosmic time machine and the most powerful space telescope ever built. In the early months of its operation, Webb observed 4 really old galaxies. Now, scientists have confirmed that they are actually the oldest galaxies we have ever observed. They're located about 13.4 billion light-years away, or about 325 million years after the Big Bang, when the universe was only 2% of its current age. Compared to Webb, Hubble brought us a view of a region about 12 billion light-years away from us. When Webb began operating using its near-infrared camera, or short, NIRCam, it detected several extreme candidates that could qualify for being the most distant. But when scientists gathered spectroscopic data, they confirmed about 4 galaxies that were almost as old as the universe itself. Due to the expansion of the universe, objects that are moving farther away from us appear redder. That's because as the universe expands, the object's light gets stretched into longer, redder wavelengths of the light spectrum. Einstein's theory of general relativity was the first to predict gravitational waves. The theory describes these waves as disturbances in the curvature of space-time. Such disturbances come from the most violent and energetic events in the universe, including the collision of neutron stars or black holes. Gravitational waves are extremely hard to detect because they're very far away, and by the time they reach us, they get weaker. The first time we officially detected such waves was in 2015, when the LIGO Observatory detected waves coming from 2 black holes crashing into each other about 1.3 billion years ago. So it took 1.3 billion years for these waves to reach us. Before this discovery, everything we knew about the universe came from studying light waves. All the matter in the universe exists in the fabric of space-time. Every massive object that accelerates produces gravitational waves carried out by space-time itself. These gravitational waves travel at the speed of light, 300,000 kilometers per second or 186,000 miles per second. And as they travel, they squeeze and stretch anything in their path. The discovery of gravitational waves gave us a new perspective. When massive objects orbit around each other, they disrupt space-time so that waves of Ripley space-time propagate in all directions away from the source. What's fascinating is that these waves travel at the speed of light, carrying information about their origin and the nature of gravity itself. Scientists have now taken a deep dive into this iconic image, finding dozens of energetic jets and outflows coming from newborn stars that were previously obscured by dust clouds. The Hubble Space Telescope has previously studied this region for years, but its optical instruments couldn't peer through the clouds. The Webb telescope, on the other hand, observes infrared light, whose long wavelengths penetrate gas clouds easier than visible light. The Space Telescope has observed infant stars interact with their environments by taking in material and then ejecting some of it from their polar regions in the form of jets. These jets create cavities in the surrounding environment and heat the hydrogen gas, causing it to emit light. Jets like these last only a brief window of time when the protostar is actively accreting. That window is just a few thousand years out of the several million it takes a star to fully form. This is one of the first images of the James Webb Space Telescope. It's a star-forming region of space known as the Cosmic Cliffs, which is part of the Carina Nebula about 7,500 light-years away from us in the Carina-Sagittarius arm of the Milky Way galaxy. The nebula is close enough to be seen with the naked eye, but is only visible in the southern hemisphere. The protostar phase is the earliest phase in the process of stellar evolution. A protostar is still gathering mass from its parent molecular cloud. Protostars form when the gas and dust in a nebula start condensing and forming clumps. As these clumps collect more and more mass, their gravitational pull increases, forcing more atoms together. This process is known as accretion and is what forms a protostar. A protostar with at least 0.08 solar masses will eventually go on to begin hydrogen burning and will join the main sequence as a normal star. But if the protostar is less massive than this, the temperature will not be enough for hydrogen burning to begin, and it will become a brown dwarf star, which is sometimes considered to be a star-planet hybrid. In 2017, LIGO and Virgo detectors observed gravitational waves coming from the merger of two neutron stars about 130 million light-years away, an event known as GW170817. When the gravitational signal came, it took an additional 1.7 seconds for light to arrive, the high-energy gamma rays from the collision. This was the official confirmation that the speed of gravitational waves equals the speed of light. You're probably wondering about that 1.7 second delay, which makes gravitational waves slightly faster than light's speed. That's likely because gravitational waves pass through matter unperturbed, whereas light interacts electromagnetically and gets slowed down very slightly. Einstein was right. Changes in gravity do spread as waves through space. In 2015, the LIGO experiment detected such waves from a collision between two black holes with masses of about 36 and 29 times that of the Sun. But the merger of these 65 solar masses in total created a remnant of just 62. So what happened to the other three? These were used to power the burst of gravitational waves in a spectacular demonstration of Einstein's famous formula, E equals mc squared, where mass and energy are equivalent. Our galaxy, the Milky Way, hosts a supermassive black hole called Sagittarius A star, about 4 million sun masses detected through the motions of stars orbiting it. This is the first image of that black hole caught a couple of months ago by the Event Horizon Telescope. However, even Sagittarius A star is fairly insignificant compared with the black holes of up to tens of billions of sun masses thought to be at the center of the largest galaxies. We currently see them through the vast amounts of electromagnetic radiation, like visible light and X-rays produced as gas falls into them. We know that this process helps them grow, but it's nevertheless mysterious. Most of the gas in galaxies moves too fast, or is too far away for the black holes to capture it. It could be the collisions between these supermassive black holes helped to grow them, especially when they were relatively young and had not yet gained much gas. However, a collision between two supermassive black holes can probably only happen if the two galaxies hosting them collide and merge too. This is an inherently rare event in the nearby universe, as galaxies are far away from each other. But it must have been much more common soon after the universe was born in the Big Bang, when galaxies were much closer together. Detecting gravitational waves from such collisions means looking back in time, observing the most distant galaxies. The Big Bang, and particularly the epoch of very rapid expansion, dubbed inflation, which many experts believe took place very soon after, must have involved enormous masses moving with almost light speed. This means that they must have produced powerful gravitational waves. However, the most powerful signal comes from masses whose size is comparable to the scale of the universe itself. Since gravitational radiation has a typical wavelength larger than the masses emitting it, the wavelength of this radiation is itself similar to the entire size of the universe. So, LIGO, or any other experiment that is smaller than the universe, will not be able to detect it.